what's it called?
Integration by parts.
Integration by parts. You'll have to do integration by parts twice in that one, the first one. And I want to talk for a moment about the derivative of something that looks like this. The one in the worksheet is a tiny bit different, but this will get to the idea of what I want to make sure you're understanding. So when you're doing your integration by parts, at some point you're going to have to take the derivative of this, and it's got an absolute value. And so we can't take a straight up derivative like we're used to doing because there's an absolute value. And what you should be thinking every time you see an absolute value is that you have a piecewise defined function. So whatever you're doing with a function that has an absolute value in it, you should be thinking pieces. You should be thinking the top piece and the bottom piece. So let's just take a look at this more carefully. The function natural log of 4 minus x, as an example, it's a piecewise function. So it's going to be equal to natural log of 4 minus x without the absolute value if 4 minus x is positive. The absolute value, if what's inside the absolute value is positive, you don't need the absolute values. But if what's inside the absolute values is negative, then you know that you have to multiply the inside by -1. If we look at a numerical example, if we do the natural log of absolute value of -2, this is not just natural log of 2, it's you take the inside and you multiply it by -1. That's what forces it to become positive. Multiplying by -1. There's not a math. Multiplying by -1 essentially is erasing the minus sign. And that's what most of us think about with the absolute value. That, oh, we just erase the minus sign that's out in front. Mathematically, to erase the minus sign, you multiply by -1. That's the mathematical thing you do. So if we multiply this by -1, now this is positive, right? That's how we take an absolute value. We multiply by -1 if what's inside happens to be negative. So now let's take the derivative. So we've got this piecewise defined function. When you take a derivative, you just take derivatives of the different pieces. And here's the part that is super cool. If we are taking the derivative of this, let's imagine taking the derivative of each piece. What is the derivative of this piece? What's the first part? 1 over 4 minus x. And then we have to multiply by -1 for the chain rule. Right? The derivative of a log is 1 divided by the inside multiplied by the derivative of the inside. Now let's take the derivative of this second one. 1 over the inside multiplied by the derivative of the inside. Derivative of the inside is just 1. So we get that. Aren't those the same? Right? If we take this -1 right here and we push it into the denominator, we will end up with 1 over x minus 4. So those are the same. So this is an interesting piece that's going to show up in the first problem in the worksheet. That if you take the derivative of a log with an absolute value, it is a piecewise defined function, but it turns out the derivative doesn't matter. The derivative will be the same regardless. So you sort of treat it like a piecewise defined function, and you discover, oh gosh, it doesn't matter if what's inside is positive or negative. This is the derivative. You do not need the pieces anymore. So that's going to be coming into play with integration by parts in the first problem in the worksheet. I also noticed in the worksheet, somehow one of my exponents disappeared, and it made the problem a lot easier. So you know which one it is? The one where there's an inverse tangent substitution. Turns out, well, there's no exponent in the denominator there was supposed to be, so it'll be really easy, which I'm sure you won't complain about. I hope. If you want it to be harder, put a 5/2 exponent on it. If you want it to be harder, put a 5/2 as the exponent. That's what it was supposed to be. But somehow it vanished. Okay, so let's get back to let's see, where are we? Why did I put that page there? Okay, we are down here somewhere, right there. We have a second example here. So let's go ahead and do this example. So here's an integration that is an improper integral. It's a function that you would never be expected to graph. If that function was on the exam, I would absolutely graph it for you. You would not be expected to graph that. Now, when we look at this, it is not jumping out at us that this is an improper integral. We have to be aware that when we plug in one of these limits of integration, we get 0. Right? When we plug in 0 for that y, e to the 0 is 1. 1 minus 1 is 0. So division by 0 is happening at that lower endpoint, the left endpoint, the lower limit of integration. And so that tells us right away that we need to convert this to limit. That tells us we have an improper integral. We convert to limit. And we convert to the limit of a definite integral. So we're going to approach c from the right-hand side, because we're moving left. So our c value we're imagining down here, it's going to approach 0. And here's our right endpoint, which is natural log of 3. So in here, this is our definite integral. We're going to integrate from c over to natural log of 3. That's a definite integral. So that will be definite. And then we take the limit of that as the c value goes to 0. So this is the whole process with an improper integral. Create a definite integral, and then take the limit. It's analogous to what you did in Calc 1 with the limit of a Riemann sum. So c up to natural log of 3. And the one important thing, remember that this is a one-sided limit. So it's c goes to 0 from the right. We're coming into 0 from the right-hand side. And then we have our integrand. And we have that. Question?
How does it determine that it's going to be one-sided?
So whenever we have a vertical unbounded region, it's always going to be a one-sided limit because we're approaching this asymptote, and we're not approaching it from both sides. So the interval that's given, 0 to ln3, is right here. It is to the right of that asymptote, so we're only coming into the asymptote from this side. So whenever we have a vertically unbounded region, we're going to approach the asymptote from within the interval. If the asymptote is to the right of the interval, we'll be approaching the asymptote from the left. If the interval is to the right of the asymptote, then we're going to approach the asymptote from the right-hand side. So we're approaching 0 from the right. If the asymptote was over here, we'd approach it from left side. And then what integration technique do we think we're going to use here? U sub. That should always be one that you just consider right off the bat if it doesn't have an immediate antiderivative. And we'll let u be what's inside the parentheses in the bottom. We'll let it be e to the y minus 1. And that's a good substitution because its derivative is the numerator. That's what makes a good u sub. For u sub to work, the derivative of u has to be present, or it's not going to work. Right? The whole idea is jigsaw puzzle. We need to fit in all the pieces of our u substitution. So if the derivative is not there, u substitution is not a good candidate. Okay, so let's go ahead and convert. And with improper integration, very similar to trigonometric substitution, we rarely convert over to U limits. It's very rare. We usually just wait to the end and go back to the original limits for trig subbing and improper integration. All right, so e to the y dy, that's du. So we have a du in the numerator. And actually, let's leave some space because we're just going to pull our denominator up. And then in the denominator, we'll have u to the 2/3, which if we pull it up to the numerator is u to the negative 2/3. And again, let's just put placeholders, put some stars in here. We'll come back in the end. All right, so power rule. Tabitha, you want to close that? She sounds awfully loud today. So we'll get u to the 1/3 multiplied by 3. Add 1 to the exponent, get a third, divide by a third. That's multiplication by 3. We have our placeholder limits. We go back to y, and we'll factor the 3 to the front. When we evaluate the limit, it's usually nice to clean up all the constants and get them out of the way. Tends to be just a little bit easier to not make some weird mistake. We're going from c over to natural log of 3. All right, so there we've integrated the definite integral. Now we just have to plug in the limits. Any question on the integration itself? So we'll plug in our upper limit. So we'll have 3 limit. And then we're going to plug in our upper limit of integration. That's natural log of 3. E to the natural log of 3 is 3. 3 minus 1 is 2. So we end up with 2 to the 1/3 power. And then we subtract off the antiderivative at the lower limit of integration. And that will be e to the c minus 1 to the 1/3. Yeah?
Sorry, I missed how you got 2 to the 1/3.
So when we plug in natural log of 3 right here, we'll have e raised to the natural log of 3. So the e and the ln cancel 3 minus 1. Exactly. Now, yeah, Federico?
It looks like you may be able to plug 0 in directly to so was there a reason you can't do that?
No reason we can't do that. So whenever we're taking a limit at a constant, so this is as c goes to 0 from the right, whenever we take a limit at a constant, we always plug the constant in first. That's our first strategy if we're taking a limit at a constant. You can't do that with infinity because infinity is not a constant. But you do that whenever you're taking the limit at a constant. You plug it in. Because the idea is that if this function in here, if it happens to be continuous at this constant, we know that a continuous function has the same value as limit. The limit of a function and the value of a function are the same if the function is continuous. So that's our first line of, that's our first strategy. So for example, if we're looking at, let me just make sure you're understanding what I'm saying. Let's compare these two situations. So let's suppose we have similar function, except this one has a hole in it and we redefine it to be that. So both those functions have domain entire real line. And if this happens to be at 1, right there, this function is continuous at 1, right? There's no gap, so it's continuous at 1. So the value of this function, let's just suppose we're dealing with x squared in both cases for the curved part. So right here, the value of the function at 1 is equal to the limit of the function at 1. So if a function is continuous, its limit and its value are the same. Whereas over here, the value of the function, let's just suppose that's up at 2. Here, the value of the function is 2, but the limit of the function as x goes to 1 is 1. So the limit and the value are different. So that's kind of what we're using. That's our background information from Calc 1. That if you have a function that happens to be continuous at the constant you're taking the limit at, the value of the function is the same as the limit of the function. So up here, like Federico said, can't we just plug in the 0? And the answer is yeah, we can plug in the 0 because when we plug in the 0, we get a number. If we get a number, that means the function is continuous there, and that's going to be the value of the limit. So the limit of a constant is itself. And then over here, we get e to the 0 minus 1, which is 0. So this tells us that this is our final answer. That is the area of that vertical unbounded region. So this vertical tail, if you will, goes up forever. It's unbounded because it goes up forever. But it approaches the y-axis fast enough that that forever piece is adding such tiny area that the area will in fact be finite.
Is there ever a situation where we would not want to take a constant out in front of the limit?
It's really just your preference.
It's just a preference.
Yeah, because a constant can factor through a limit or a derivative or an integral. So sometimes you would leave it in maybe if there's going to be cancellation from plugging in one of these bounds. But yeah, you could either way, it's going to come out the same. Yeah. One thing I said on Tuesday was the process should confirm what our intuition is. And most of the ones we talked about on Tuesday, we were looking at a power of x in the denominator. And so we could really build intuition. If the power of x in the denominator was bigger than 1, we had horizontal convergence and vertical divergence. And if the power in x was less than 1, we had horizontal divergence and vertical convergence. This is a little different. When we look at this function here, it's not totally obvious. There's not quite the same way to build intuition here, because we have exponential function, an exponential to the 2/3 and an exponential to the 1. So it's not quite as obvious. Powers of x, though, should be more intuitive. So let's do one more example here. We've got, this one's going to be an integration by parts. So we've got this sleepy little function here going down to the x-axis. When we look at it, it looks like it's drifting down kind of slowly. Right? It doesn't look quite as quick as if it was just 1 over x squared, which we've looked at. 1 over x squared turned into a 1 as the area. And 1 over x squareds look like it approaches the x-axis really fast. This one feels kind of ambiguous. It's like, ooh, is it approaching it fast enough? The graph isn't as definitive as it could be in some other cases. But here's what I want you to think about. So we already did 1 over x squared. That was the very first example that we did, and the area was 1. So when we look at that denominator, if the natural log was not there, we know it would converge. It would converge to 1. So the natural log in the numerator is growing towards infinity. So there's a struggle between the x squared going to infinity and the natural log going to infinity. And the question is, which one's going to win? If the x squared could go to infinity fast enough that the numerator going to infinity just doesn't matter and we'll still get convergence. If the numerator was a constant, obviously it would converge because the constant's not going to affect the rate at which x squared goes to infinity in the denominator. But you see the tug of war? This is going to infinity, that's going to infinity. And so it's kind of, okay, well, there's a little bit of a struggle. If this one wins, then we're going to have finite area. If that one wins, then we're going to have infinite area. So there's a little struggle. It's not obvious. When it's just powers of x, we can say if the power of x is bigger than 1, it's going to converge horizontally. But we've got more going on. So we've got to look at it. So certainly we know it's improper. So we're going to do the limit as b goes to infinity, 1 to b. So that, what we've done is turned it into the limit of a definite integral. So we're imagining our b right wherever. We'll just put a picture right there. So when we put in this b, there is our definite integral right in front of us. And this definite integral is going to end up being a function of b. When we integrate from 1 to b, if you've got a variable up there, you always end up with a function. You don't end up with a constant. So that's going to give us a function of b that we then take the limit as b goes to infinity. Okay. And integration by parts is how we're going to have to do this. We can't let u equal natural log of x and have u substitution work because the derivative of natural log of x is 1 over x, and we don't have 1 over x, we have 1 over x squared. So u sub's not going to work. The derivative is not present. So it's close, but not quite. So we're going to go with ultraviolet voodoo. We're going to let u be natural log of x because we want to let u be natural log of x, because if we put the natural log of x with the dv, we don't have an instant antiderivative that most of us know. So it makes more sense to put the u equal natural log of x because we can differentiate natural log very easily. That'll be 1 over x dx, and this will be minus 1 over x when we integrate. So integrating x to the negative 2, we add 1 to the exponent, we get x to the negative 1. And then we divide by negative 1. So negative x to the negative 1 is negative 1 over x. Cameron?
Why is it x to the negative 2?
When we have a power of x in the denominator, to integrate it, you move it up to the numerator so that you have a constant in the exponent that you can add 1 to and then divide by the new exponent. So you can use the power rule. Anytime we have a power of x down below, right, we pull it up so we can integrate it with the power rule. Except in one case, when x is just to the first power, integral of 1 over x, we cannot do that. Integral of 1 over x is natural log. But you can't do that there. If you have 1 over x, the antiderivative is natural log of absolute x. If you pull that x to the numerator, what happens when you add 1 and divide by the new exponent? Divide by 0. So that's the one exception. There's always an exception in math. Almost always. All right, so then we're going to do our ultraviolet voodoo stuff. So the limit is just lingering out in front, waiting to be evaluated at the very end. This is going to become uv, which is the main diagonal. So that's going to be minus natural log of x over x. And that's from 1 to b. We're going to take the limit of this whole thing. So there's uv, main diagonal, minus the integral of v du, same limits of integration. v du v du is negative, and that negative times this negative will make a positive. And it looks like 1 over x squared, which is x to the negative 2. So that is the bottom row. So like we always do, main diagonal minus the bottom row. That is integrable. We do have to evaluate this front expression between 1 and b, but we can just wait to the very end. Let's do all of our substitution in at the very end. Let's just be patient. So we have minus natural log of x divided by x. Integrate x to the negative 2. We just did it up there. Add 1, get x to the negative 1. Divide by negative 1, so we get negative 1 over x. Same as we just had above. So there is where we're at. We're going to plug in our upper and lower limits. Figure out the victor. Do we have convergence or do we have divergence? Good over evil. So we have negative natural log of b divided by b. minus 1 over b. And now we subtract off the antiderivative evaluated at 1. Subtracting off a negative turns into addition. Natural log of 1 is 0. So we're going to have plus 0 and plus 1. Subtracting off antiderivative at 1. One over b. As b shoots off to infinity, where does 1 over b go? 0, for sure. And limit of 1 is 1. Limit of a constant is itself. Natural log of b over b. That's indeterminate. Because you have infinity over infinity. Indeterminate. What was our calculus 1 strategy if you had an indeterminate form when you're taking a limit? L'Hopital's rule. So L'Hopital's rule, let's talk about that for a minute. When we look at this fraction, we are thinking of the numerator and denominator independently. We are saying the numerator goes to infinity, the denominator goes to infinity. What is the best linear approximation to a function? The tangent line, so the derivative. So if we think about the quotient of two functions, that quotient should approach the same thing as the quotient of the two best approximations. If we take the best approximation for the numerator and the best approximation for the denominator, the reason that they're best approximations is that they're going to behave similar to the function. So if the quotient of functions is going somewhere, if it's going to have a limit, the quotient of tangent lines should have the same limit. The quotient of functions and the quotient of best approximations should be the same. Otherwise, those approximations aren't very good. So we use, and that's what L'Hopital's rule is. L'Hopital's rule says that if you have a quotient of functions and you can't evaluate the limit, consider the quotient of tangent lines. So we're going to take the derivative of the numerator, which is 1 over b, and the derivative of the denominator, which is just 1, and we have that. And that one is evaluatable. We can't evaluate that. When b goes to infinity, where does this fraction go? 0. So that whole thing's going to go to 0. We can't evaluate it. And so then we're going to end up with 1. So therefore, we have convergence. So therefore, the interval converges. The improper integral converges. Get 1. All right, any part of the evaluation process there that you want to ask a question about? Yeah?
Still just kind of lost on going from the natural log of b over b to 1 over b over 1.
What's the derivative of natural log of b with respect to b?
1 over b.
What's the derivative of b?
This is 1.
1.
Okay, so you can just, right, you can think of it as,
So yeah, we're just treating them individually like their own functions, right?
okay.
So the derivative of b is 1. The derivative of natural log of b is 1 over b.
Okay, and the reason we do that is because, right, this,
So this is an indeterminate form. It's infinity over infinity. As b goes to infinity, natural log goes to infinity, and b goes to infinity. So it's indeterminate. So we had that group of indeterminate forms back in Calc 1, infinity over infinity, 0 over 0. So those are indeterminate because we can't tell. We don't know which one's going to infinity faster. Now, let's think about this intuitively for a minute. When you think about the natural log function going to infinity, it's going very slow. When you think about the denominator going to infinity, y equals x, essentially, right? We're talking about y equals b, y equals x, whatever, however you want to think of it. It's the identity function. That goes to infinity way faster than natural log goes to infinity. That's why this limit's going to be 0. because the denominator is going to go to infinity much faster than the numerator is going to go to infinity. So then, right, so that's going to drag it to 0. So we can think of it that way also. But the math of it is using L'Hopital's rule, which says quotient of functions will approach the same thing as the quotient of derivatives. So we're thinking about these individually. We have a quotient of two functions. We take the derivative of each. And that's what L'Hopital's rule says. Nick?
So is it like a reliable method to like figure out the behavior of whatever you're trying to do that? Like if I know natural log of x approaches infinity slower than just x, I can get.
So there are going to be some cases where we can't apply L'Hopital's rule.
Okay.
And we have to use, like we're going to see some functions in the coming chapters that we don't have immediate derivatives of. For example, if you have a power tower, if you have something like that, that's called a power tower, we don't know how to differentiate that readily. And so, but we are going to be able to sort of use this kind of heuristic argument that that's going to go to infinity wicked fast, x to the x. So we'll use that kind of argument that, so if we had something like, an exponential divided by x to the x, a power tower is going to go to infinity much faster than an exponential. So if we were going to take the limit of this as x goes to infinity, we'll get 0. But we don't, at this stage, we don't have mathematical tools to do it like L'Hopital's rule, because we don't have a way to differentiate a power tower. And we're going to have some other functions like factorial. And same idea. A factorial goes to infinity wicked fast, faster than an exponential, but we don't have a way to differentiate a factorial. So we're going to have to use this heuristic argument that, the factorial goes faster than e to the x to the infinity, so the limit will be infinity here. But when we have functions that we can differentiate, we go and we do the math if we can. So we only resort to this sort of which one goes faster argument if we can't take derivatives.
So
But we'll get to that.
it's just one of those things we have to, like, looking for use of or log form. It's just one of those things we look for the intuition of something.
Sure, absolutely.
Okay.
Yeah. Yeah, and in thinking of graphs, that's why graphing is so important, because it kind of gives you a visual. You can visualize the natural log function going to infinity very slowly, and you can visualize y equals x going to infinity much faster. Like that difference between the two is big. Okay, so another weird thing, do I even want to point this out? So when we integrated 1 over x squared from 1 to infinity, what did we get? 1. And now we're integrating natural log of x over x squared and getting 1. Deal with it. Okay, so here is our summary. So the summary, we're going to base it on powers of x, because this is where we can really generate intuition for when we have convergence and divergence. Powers of x. And so most of the time, let's go down to the graph here. Let's go down the graph. So the black curve is 1 over x. That is going to have a tail horizontally from 1 to infinity that diverges. It's also going to have a vertical tail that diverges. So 1 over x diverges both vertically and horizontally. That is going to be our threshold function. If we approach the x-axis faster than 1 over x, we will have horizontal convergence. So the red function, we bumped up the power of x just a tiny bit, and we'll have convergence. As long as that exponent is more than 1, if it's 1.000001, that's enough. If it's just a skosh bigger than 1, that curve is going to approach the x-axis fast enough for convergence. If that x is bigger than 1, we'll have a finite horizontal tail, we'll have convergence. But this is that whack-a-mole type of thing. If the curve goes to the x-axis fast, it's going to pull off of the y-axis, and we're going to have vertical divergence. So if we bump the power up a little bit, horizontal convergence, vertical divergence. You can see it from the picture. If the black curve already diverges up here, and the red curve's even further away, there's more area. And more than infinite is infinite. The blue curve, we bump the power down just a skosh, so x to the 1, bump it down to x to the 0.9. And we have the opposite situation. Now, that's going to peel the blue curve off the x-axis. It's going to converge to x even slower, converge to the x-axis even slower, but it's going to come into the y-axis really quickly. So if we go down below 1, even just a tiny micro amount, 0.999999, that will have convergence vertically and divergence horizontally. So the function 1 over x is going to be that sort of threshold function, and we're going to look in the denominator and compare the exponent to 1. Bigger than 1, converge this way, diverge that way. Less than 1, diverge this way, converge that way. So they're just kind of opposites. Now the place that you're going to use this in the nearest future, in the soonest from now, will be when you get into differential equations and you study these things called Laplace transforms. So a Laplace transform is an improper integral. So we are going 0 to infinity here. I think I mentioned this on Tuesday. I'll just say it again quickly. If you have a function that's discontinuous, you can't integrate it. And so it's very common when you're dealing with engineering type stuff to have functions that look like this. They call them step functions. Up, down, on, off. Clearly it's discontinuous. You have all these points of discontinuity. And you can't take a derivative of a discontinuous function, right? That's a problem. And so what the Laplace transform does is it takes a discontinuous function, and when you multiply it by this e to the negative st, this exponential decay function, this strange function, what it does is it turns a discontinuous function into a continuous function. So then they call it the Laplace domain or the S domain, you can take derivatives all of a sudden. And so the idea is that, we've got this, and that's a very common function, right, with electricity, back and forth, on, off, on, off, on, off. Very common function, and we can't take a derivative, but if you Laplace it, you can take the derivative in the Laplace domain, do some math, and then you can bring it back to the original domain.
When you multiply it by that e to the power negative st, does that change the function itself?
Yes. Yeah, so it changes the integrand. So we can't do anything with just f, so we multiply f by e to the minus st, and it totally changes the nature of this. It turns it into a continuous function.
So how would the derivatives, or how would that be relative to the function?
Because there's something called the inverse Laplace transform. So you do the Laplace transform to get over to the S domain, you do a bunch of math, and then you take the inverse Laplace and you come back to reality. And it works. That's why we do it, because it works, which is, you'll learn all about it when you get into engineering courses. The Laplace transform is super common, super important. Okay, so let's go to our final chapter for this unit. We are going to talk about the very basics of differential equations. And the reason that we do a couple of sections in here is that the way you solve a differential equation is by integrating. So we're going to do the most simple differential equations just to sort of get the concepts down that, oh gosh, integration is how you solve a differential equation. So that's kind of, it's not going to be difficult. You have to put in enough time that you can follow the steps, but you'll find that these are pretty easy, these basic differential equations. So you can read that paragraph when you have time. The gist of that paragraph is that every field in science uses differential equations. If there was one topic that was uniform across all fields, it's differential equations. Because a differential equation is something that measures change. And you can do that empirically. You can go out into the field and measure how a population is changing. You can look at money in the stock market and see how the returns are changing. Like there's rates of change you can go out and measure. Like that's what we do. We measure rates of change, and then we try to find a function that has that rate of change, and we can do math on the function to predict the rates of change. So that's the big idea. So the idea is that we go out in the world and we can construct these differential equations. We can build them by looking at empirical data. But then we want a function that satisfies it because then we want to predict the future, right? That's always our goal, is to predict the future. And that's what functions will do. They'll predict the future. So if we can find the function that satisfies this differential equation, then we can predict what's going to happen in the future. Same here. So with the differential equation, the first thing we do is talk about the order. And the order is just the highest derivative that appears. So when we look at this differential equation here, there's just a first order derivative. So that's a first order differential equation. When we look at this differential equation, we have a second derivative and a first derivative, and a zeroth derivative, if you will. The function itself is the zeroth derivative, y to the 1. So here we have the function and its derivative. Here we have the function and its first derivative and its second derivative. So the function y is what we're trying to find here. We want to find the function y that satisfies this derivative equation. And first order, second order. And the next big word that you hear all the time is linear. And as you get into higher and higher math classes, the word linear means something different in every class. So in differential equations, linear means that the derivative, any derivative, and the function are only raised to the first power. So we don't have y prime squared. We don't have the square root of y. We don't have y times y double prime. We don't have y divided by y double prime. So for a differential equation to be linear, the function and all of its derivatives have to be raised to the first power. We can't have any commingling of the dependent variable and its derivatives. So y and its derivatives have to just be to the first power. So that's linear. You can't have y times y prime. So it's got to be as simple as possible. We've got the function, we've got its derivative, but we don't have any weird powers on there. With these t's, all bets are off. These can be as wild and crazy as you can imagine. You can have square root of t, you can have inverse tangent of t, you can have 1 over t to the 5, doesn't matter. The t's don't matter. Whether it's linear or not only depends on the dependent variable, on the y. So y is the dependent variable, t is the independent variable. Okay, so that's just some terminology. And let's look at a couple of examples. So right here, this is a differential equation. It is a first order differential equation because we see that the highest derivative is just the first derivative. And it is linear because the y and the y prime are not raised to any powers. They're not multiplied by each other. They're not divided by each other. Right? There's no funny business. It's just y and y prime. There's no commingling with the derivative and the function. So that's a linear first order. And here, what they're saying is they claim that that function satisfies the differential equation. And we want to show that it does. In general, there will be an infinite number of solutions to a differential equation. Just like when you integrate any function, you get that constant of integration. If you integrate x squared and get x cubed over 3 plus c, you have an infinite collection of antiderivatives. Right? The indefinite integral represents an infinite collection of antiderivatives. When you integrate x cubed and get x to the 4th over 4 plus c, right, this is a family of antiderivatives. There's an infinite collection. Right? Every value of c gives you a different antiderivative. And sometimes, which we did earlier in this class, sometimes you can find the c. Sometimes you're interested in exactly 1. Sometimes they give you some sort of initial value, and you can find the one antiderivative that satisfies your initial condition. But a lot of times they just say find the family of antiderivatives. And that's what an indefinite integral does. An indefinite integral finds you a family of curves. Okay, so let's show that this function satisfies that. So at this stage, we haven't said how to find this function. We're just saying that function is going to satisfy this. So we plug it and its derivatives in and see if it works. So if we have y equals a constant times t cubed, its derivative is going to be 3ct squared. And it's as simple as it sounds. We just plug those in and see if we get something that's true. Just like back in algebra when they said, determine if this point is on your curve. All you did was plug in the coordinates and see if it worked. Same idea. Nothing complicated. So we have t times y prime, so t times this, minus 3 times the y function, which is ct cubed. And we put a little question mark there. It will satisfy this differential equation if we get an identity. Let's see, do we get an identity? Yeah, those things cancel. We get 0 equals 0. So that checks, so therefore it is a solution. And one obvious question is, could there be other solutions? Or is that unique? This is an infinite collection of antiderivatives, or infinite collection of solutions. Let's call them that for now. And so if you plug in 2t cubed, it will work. If you plug in 5t cubed, it will work. If you plug in 10t cubed, it will work. And so the question is, are there other forms? Bless you. Are there other forms, or do the only functions that satisfy this have to be constants times t cubed? And the answer is that there's something called the existence and uniqueness theorem in differential equations. And you will learn in differential equations a way to analyze the coefficients here, and you'll be able to determine. Most often, you're interested in things that have a unique solution, and you'll figure out whether this is in fact unique or not. In this case, it will be. We won't talk about why, but. So this tells us, if it is unique, that every solution has to be of this form. Has to be a constant times t cubed. Can't have a quadratic that works. Can't have a quartic that works. Can't have a sine that works. Has to be that form.
So how did you, why did you multiply it by t and then by...
Because that's what the equation says to do here. This says t times y prime. So t times y prime. And this is 3ct cubed when you combine the t's.
Okay.
So you get 3ct cubed minus 3ct cubed, which is 0. Yeah. So we're just doing what the equation is telling us to do. So for example, here, this one, our function that they say is the solution to that second order linear. So this dE second order linear. And here's an example where they give us some initial values. So we can figure out what the C is. So let's see what happens here. So they tell us that y is that. So let's figure out y prime. Derivative of cosine is minus sine, so that'll turn into a plus. So that'll be y prime. And this equation is second order, so we need a second derivative. Derivative of sine is cosine, and then we use the chain rule. So that will be our second derivative. All right, so let's first confirm. There's two things happening here. Here we have our differential equation, but we also have these initial values. And so notice that they gave us a specific function with no constant. So let's make sure that our initial values are true for each of for the function and its derivative, because that's where the initial values are. So let's double check that. So that's one way it could go wrong. They could give us a solution, the differential equation, but they could be fooling us with the initial conditions. Let's just make sure. So let's check these conditions. When we do y of 0, that means we're plugging in 0 right there. So y of 0 means minus 3 cosine of 0. And that is going to be minus 3 cosine of 0 is 1. And so this checks, right? Because this says y of 0 is negative 3, and that's what they gave us. So the initial condition for the y function is good. Bless you. Let's check the initial condition for the derivative. So we're coming down to our derivative right there. So that's going to be 9 sine of 3 times 0, which is 9 sine of 0. And 9, what's sine of 0? 0. So this is 0. So that's checking also. So we just confirmed that both those initial conditions are working for this function.
When you took the derivative,
Yep.
what happened to the negative?
Because the derivative of cosine is negative sine. So the minuses combine. Okay, so we've confirmed the initial conditions are valid. Now let's check that the equation is valid. So now that we have the function and its derivatives, we can plug them into the formula here. So it says y double prime plus 9 times, y, not y double prime, not y prime. So we have that. Does that equal, so big question, is it 0? So this is our last step, is to confirm that this gives us an identity. And sure enough, that's 27 cosine of 3t minus 27. So we do get 0 equals 0. So that checks. So in the first one, we were only given a differential equation to check. We only had to do the checking of the equation because they gave us a general solution. Here, they're giving us a specific solution. They've told us that the constants have been resolved here. So we have two things to check: the equation, and we have to make sure that those initial conditions are valid. So nothing too complicated at this point. We're just sort of saying, okay, the big takeaway at this moment is that the solution to a differential equation is a function. Right? That's what we're doing. We're checking the function and its derivatives to see if they actually do work. We haven't talked about how you find that function yet. Now, you all can solve basic differential equations. When you want to solve this equation right here, all we're going to do is integrate both sides. What's the integral of y prime? Y. So if you have a derivative that's explicit like this, then all we're doing is integrating. So if we want to solve this differential equation, we integrate both sides. So we integrate, and let me write it this way. So y prime of t is dy dt, correct? And when you integrate, let me change the colors on this just to try to point something out. When we integrate, remember that the integral comes along with its differential. That's one thing. Right? The integral cannot be separated from its differential. All right, so if we integrate the left side, we have to say, well, with respect to what letter? The integral with respect to dt looks like this. The integral with respect to dx looks like this, right? Depending on what the letter is. So the integral and its differential, the differential is just sort of a clue that we're integrating with respect to t, but it comes together. It comes as a package. And so on the other side, we do the same thing. We're going to integrate this function with respect to t. Well, on the left side, these dt's just cancel, and the integral of dy is y. And then on the right side, we'll do our regular old integration. The integral of an exponential is itself divided by the derivative of the exponent. And then we have our constant of integration. So this is a general solution. Maybe I should say the general solution. So the general solution, it's called general because we have this c. It's general. If we want a specific solution, which in DE you're going to call a particular solution, if you want a particular solution, you would have to have some initial value so that you could plug in. So maybe they say y of 0 is 5. Then you plug in t equals 0, y is 5, figure out what c has to be, and then you'll get a particular solution. You'll get one from this infinite family of antiderivatives. So the general solution is always this infinite collection of antiderivatives. And if you want one single particular one, you need some initial value. So whenever you see general, it's going to have a plus c in it. So you've already done this. So you've been solving differential equations all along. Now, this detail right here, we usually don't write it out in practice. We just sort of think to ourselves, oh, the integral of the derivative is the function. It gets a little tedious if you're going to write this, especially if you start having second order and you're going to write that in differential notation. So here's what we'll do. So the first derivative, if we integrate the left, you integrate the second derivative, you get up to the first derivative. And we just do it like this. We don't write those little nitty-gritty details because they're so tedious. But we're doing the same thing that we did above. We're integrating both sides with respect to t. And we saw above that when you integrate with respect to t, you just get the next level. If you integrate y prime, you get y. If you integrate y double prime, you get y prime. So that's going to be the left side, just y prime. The right side is the integral of the right side. We integrate that with respect to t. Power rule again. So we add 1 and we get -2. Divide by -2. And then there's our constant of integration, which makes it a general solution. And we know we're going to have to integrate twice. So let's put a little subscript on there because we know there's going to be another constant of integration with the next integral. Okay, so there's y prime. And I guess we can stay with that color. So we integrate again. So now y will be the integral of this. So it's very similar to what we did back in the first chapter that we did together. Start with acceleration, you integrate twice to get to position. Same idea. And so the function that we're looking for, add 1 to the exponent, divide. Add 1 to the exponent, divide. That's 2. Add 1 to the exponent and divide. Add 1 to the exponent and divide. That is our solution, our general solution. So once again, with the general solution, we're going to see that you have constants. If it's a second order, you'll have 2 constants of integration. And if you wanted to resolve them, you'd need some initial value, a couple of initial values.
Where did the t and t plus c2, where did that come from?
So when you integrate a constant, you get that constant times t. So we're integrating. So if you wanted to, you could think of this as multiplied by t to the 0. If you add 1, you get t to the 1 divided by 1. But in general, if you integrate a constant, you're going to get that constant multiplied by the independent variable. Yeah. And then the c2 is the constant of integration for the second integral. All right, any questions on any of the concepts so far? All right, question?
So like, what makes these hard when you really start doing them?
So the easiest are first order linear. The second easiest are second order linear. And then they get hard when you have first order nonlinear, second order nonlinear. So as soon as we get to nonlinear, it gets way complicated.
Okay.
So, and the technique that we're going to learn in 9.3 is kind of the simplest, nicest scenario we're going to call separation of variables. And it'll be, you will not find it difficult. Yeah. But as soon as you get into a DE class, like this will be done the first day, and then it gets hard. As soon as you go to nonlinear, even if you have linear, you can have linear ones that are complicated where you have solutions that are exponentials or trig functions, and you have all sorts of. But in general, when you get to differential equations, you will find it easier than Calc 2 or Calc 3. There's very few people that would find DE harder than Calc 2 or Calc 3. All right. So that's good. You've got that to look forward to. That math's going to, plateau Calc 2, Calc 3, and that's going to get a little easier. It's important to know that. If someone says that Calc 2 is hard, Calc 3 is hard, and linear algebra and diffie-q are just as hard, that's painful to think about. But knowing that it does crest and that it gets a little easier, linear algebra is even easier than differential equations. So.
Just a little confused on the C's, the two C's.
Mm-hmm.
They just.
So anytime we do an indefinite integral, right, we have a constant of integration.
Right.
Because this could be a 2, could be a 5, could be a 10. If you take that derivative, it will be x cubed no matter what constant you're picking. So there's always a constant of integration anytime we do an integral. So we did an integral here. There's the constant of integration for that integral. And then we integrate it again. Well, that integral has to have a constant also.
Okay.
So if we had a third order differential equation, how many constants of integration are we going to have? 3. If you have a fourth order, you'd have 4. And so if we had a fourth order differential equation, we know there's going to be 4 constants of integration. In order to get a particular solution, you would have to have how many initial values? Let's go back up here for a second. So I think it was on the prior slide. So right here, second order differential equation, we had to have two initial values in order to get the particular solution. So if you have a fourth order, you would have to have 4. All right, let's take a break. Let's take a 10-minute break. And if anyone has questions? Questions on the worksheet? Oh. This? Oh. No, we did the first slide. Yeah, you came in a little bit after. If you look at, where did I put it? There's the first problem on the worksheet is kind of the trickiest. And
Do you love doing that to us, don't you?
I do. Start out, ease up. So you have to understand this for the first worksheet.
Okay, can I take a picture of that?
Absolutely. Yeah, it's on there.
What slide?
It's on the very last slide for the chapter 8 stuff. I'll title it in a minute.
Oh,
but
wait, didn't we just do this last class?
We have talked about it, but not quite so specifically. So this is trying to find the derivative of a natural log of an absolute value. Absolute value is piecewise defined function, so this is either equal to that if what's inside is positive, and it's equal to this if what's inside is negative. So if this is negative inside, the way we get rid of the absolute values is to multiply by -1. So we have plus x and minus 4.
Oh yeah, we did that at some point on one of the.
We did. Yeah. And then if you take the derivative of this one, it's 1 over the inside times the derivative of the inside. Same thing here. And what you notice is that they're the same. That -1 can distribute to the denominator, give you plus x. So even though you have this absolute value in here, its derivative is really just a single function. It's not a piecewise function as you may think.
Why would you need to do that whole process? Is the question asking for the whole process?
No, the question is not asking for the process, but you have to do integration by parts, and this is going to be your u. That's going to be its derivative. This is just to justify that that's the derivative, just so that. But it's not obvious. When you look at an absolute value, there's no, like you can't just add 1 to the exponent and divide. There's no process other than doing this and then noticing that they're the same. Because there are some cases where you take the derivative of a piecewise function and it really does matter. And you end up with different derivatives. Like usually a piecewise function would give you different derivatives, but a natural log of an absolute value won't.
It like started going and it just stopped.
Well, let me film all that.
You might get scared if you want. What do you want to be?
So does the black line here converge on both?
Like, do you want to feel comfortable by saying them out, or do you want to like?
So you have to make this point.
Let me tell you a scary story.
Exponent of x is
have to make it at least 24 hours in advance. They don't let you make same day. Make sure you have
So it has the black one would have the
As you're working. You're like, fuck, I've been smoking weed all week.
I'm sorry, I didn't mean to touch it.
No, you're good.
What happens in the area comes this way and that way, they towards the left and
Yeah.
converge this way.
I haven't
So
started
if I have that right,
No, that makes sense.
Yeah, I haven't done that shit. This is,
My math professor in trig, like when I was in trig, she like.
yeah, I can show you.
She could
Cause I have started.
touchscreen or not, so she was like, I didn't have a touchscreen at the time, so she would just like come up and she would like scroll and like nothing would happen. Like, oh, I never tell anymore. Well,
The touch screen is so cool.
yeah, I love it. I was
I
just.
did not mean to touch that.
You're good. No, it's fine. Yeah, I really like this laptop actually. Which like usually I'm kind of in about everything, but
Okay, I started,
this laptop I'm like.
and then yesterday I spent half an hour.
Part of it's just design too. It's got like an OLED screen, like the colors are just very colory.
Very colory.
Yeah. Tell me that ain't a colory color.
That is a colory color.
So you wanna be
It's got like
scared of
really,
it?
yeah, I like it. It's just bad.
Well, you just know. My
If I do that, my battery dies. My battery dies in like 2 hours. Not even 2 hours.
Dad will never forget.
See that has permanent damage right here.
Really?
Yeah, on my
Every once in a while.
What CPU?
Hey, it's like,
It's a 5600. It's a AMD.
Yeah. That's crazy.
and there's nothing to do with
It's
it.
a,
That's it.
the display's 144.
Yeah.
But
Can you turn that down?
I might be able to, but then it also.
Really?
Nah, I'm just used to 240 hertz or 144.
Yeah, I like
That's not too
on my desktop.
Because this shit was like
I
dumb.
didn't know this would go like 2 to be honest. But I was like, it's a laptop. How
Oh yeah, it
realistic
doesn't
is
have to be.
You're excited about that?
I like mine because it's got like the style. It came with the stylus. It came with your sleeve.
How much is your for?
How much I paid? 12 or 13.
What's the
Go on.
CPU?
I don't think we have What the fuck is this?
More than those.
It's like 100%
This is my first time opening Casman Windows 11. The same class. It's at 7/12/55.
Not my time.
And then she's on the graphics card. Yeah, it's got 1 terabyte SSD.
I asked if they could.
So it's pretty easy.
Yeah, that's what it was. So I also like trying to put it in there.
Like, I don't know, so I was, like, whenever I was buying this, I like wanted it to run engineering software. Really need, like, if this absolutely cannot run it, I can just go with it and run it.
There's no way.
We got like what?
Yeah, you can fire him a lot.
She got. She's
She gets a job next year.
Yeah, I remember.
Where she works, she would do.
Actually, I've been cross-sector.
I'm an ass.
That's good. Honestly, I kill pockets for this very fucking much.
I was trying to be Greco. I did
I don't think that's
I was on either.
I've been saying it for years. They let it.
I never, I like, the way I wrestle my joints is I always do like upper ones.
Hey, you want?
Yeah, so I was like,
It's funny because it gets high every day and has high
The absolute value. It's
like
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 because
he got an internship with
the absolute value is
and
multiplying by like the linear. It's like actual and that's like the same thing of x minus or sorry, 4 minus x. And so it, like that is like that explains
Mediocre. You'll get there.
like you get that instinct. I don't know. One person.
Oh, yeah, yeah, I would definitely.
I think the whole thing. The question it's like any results. So when the
I'm sure it just like
it is like 4 minus x.
Here I go.
Oh, shucks. I never hit pause.
there's a certain point in the skill curve.
Yes. This one, in the problem, this one though, we're going to convert it first to linear. And use a log
Power
curve.
by 2 in the integral every time you control it.
So how does
Like you have a power of 4, you'll do it twice. But it's a matter of just letting you understand, but
Yes, yep, exactly. And then you have that log product. You have the log product.
That's terrifying. Going down to
How do you separate that?
It takes a little bit.
And then you're taking less. So, well, then you're going to do integral with parts. You know.
You would not do that like in a crowd. Like I'm thinking
All right, let's finish up our differential equations. All right, so this is not just a differential equation, but it also we've been given an initial value. So usually they call these initial value problems, IVPs, initial value problems. So we can do what we normally do. On the left side, we have the derivative. On the right side, we have a function. If we integrate both sides, we'll go from y prime to y. So we're integrating both sides here. Integral on the left, integral of y prime is y. And then integral of the right, we have sine of t plus cosine of 2t times dt. And we do exactly what you think we're going to do. We integrate term by term, and then we're going to plug in that initial value and solve for c. So let's go ahead and do that. So the integral of sine is minus cosine. The integral of cosine is sine with RCR divided by 2. Yeah?
Okay, this is like probably a really dumb question, but like.
Then say it really loud.
But like, why are we taking the antiderivative or the integral? Like, you probably already answered.
Well, that's okay. So we want to undo this derivative.
Okay.
And the way we undo a derivative is to take an integral. And so if we do something to one side, we have to do it to the other. So we're essentially doing the integral of both sides. That's what we're doing.
So like with the other
Mhm.
previous equation that we did before break, like go down a little bit.
Down here?
Or
So here, if we integrate y double prime, we get to y single prime. And if we integrate y single prime, we get to y.
Okay.
So we're going to do two integrals here. So here's our first integral. There's the antiderivative. But we're only at y prime, and our goal is to get to y, so we have to take one more antiderivative. Does that make sense?
Yeah.
Okay, sure. Okay, so any questions on the antiderivative? Integral of cosine is sine divided by the derivative of the angle. All right. So there is our, this is called the general solution. So the general solution has the C or C's, depending on the order. And now we want to get to our particular solution. So the particular solution is found by using the initial value. This is going to give us our particular solution. So when t is 0, y is 4. So we're plugging in 4 for y, and we're plugging in 0 for the t values. So we are going to have this expression right there. So this is the initial value. And on the right-hand side, we get 4 equals minus 1 plus 0 plus c. Sine of 0 is 0. So this tells us that our constant is going to be 5 for this initial condition. So therefore, our particular solution will look like this. So that is our particular solution. So for the most part, this first section is just putting words to a lot of things we've already done. All right, we're calling these, we're giving the, we're calling that a first order differential equation that's linear. It's got some initial value, so we're getting a particular solution. We haven't called it that before. So it's nothing too complicated yet. All right, so another second order. So this second order initial value problem, we've got two initial values. Second order differential equation. And it is definitely linear. All we have in it is y double prime. There's not even a y or a y prime. And that is raised to the first power. All right, so we integrate both sides. The integral of y double prime is y prime. That's going to be t e to the t dt. That integrand is a product. So what technique of integration makes the most sense? Parts. So we'll let u be t, and we'll let dv be e to the t. And then in the derivative column, we take the derivative of both sides, and we'll end up with du equals dt. The integral side will end up with v equals e to the t. So uv is the main diagonal, so that's t e to the t. Minus the integral of the bottom row. And this is still y prime. So we've done one integration so far. So let's finish off y prime. So this will be t e to the t minus e to the t plus integration constant. Here we'll put a C1 because we know we have a second order. We're going to have two constants. So So now we have an expression for y prime. We have a general y prime. Integrate both sides again. So if we integrate the left side, we will get up to y. That happened later today than it has in the past. Does that mean the whole thing's just going to die at some point?
Keep you going.
Feels like, why is it just one blip? One blip per day. It just seems, there's got to be a reason. Okay, so we have again an integral of t e to the t, which we already did. Question?
Are we allowed to like solve for C1 right now, or do you have to wait?
We could. We could. We could use the initial value for the derivative and plug that in here and solve for C1 right away. Yeah, we could. It's your preference. You could wait to the very end and go solve for both of them when you're solving, or you could do it right now. What do you want to do? Wait till the end? It doesn't matter. Either way is totally fine. Doesn't matter. Because we will use this equation to solve for C1 when we do it. Yeah. So yeah, it's a totally reasonable thing to solve for it right now. Say, hey, I don't want a constant in there. Let's get rid of it and turn it into a number right away. Totally that's a good way to go. Let's see, we need this thing right there. Okay. So the integral here, integral of t e to the t, that's this whole thing. Okay, we just integrated t e to the t a moment ago. Right, that's t e to the t right there, so that's going to be this. So we're going to have t e to the t minus e to the t. And then we integrate negative e to the t, so that's going to be just itself. And then we integrate c1 to get c1t, and then we have our second constant of integration. And so a lot of questions, one reason you might not want to solve for that constant in the middle of the problem is that a lot of times they're going to say, what is the general solution for y? The general solution. So the general solution is going to have both constants in it. So if they want the general solution, then you wouldn't want to hop out and solve for that constant yet. So this is the general. The general solution always has the constants, you know, the c's in there. So that's our general. And we could do a combination here, right? What's that going to be? Minus 2 e to the t. We could combine those two like terms. So we would write this as minus 2 e to the t plus c1t plus c2. That would be a better way to... Well, let me grab that, just the box, or is that going to grab the whole thing? The whole thing, yeah.
I think just click on the box.
Yeah, I tried to do that, and it felt like it wasn't wanting me to do that. So I panicked. That will work, right? Okay, so there's our general. And then if we want to get our particular, so the particular has initial values, let's see, y prime of 0 is 1. So we're going to come up here. So this is y prime right there. So y prime of 0, that is not very good. Y prime of 0 is 1. So that means we're going to plug in 1 for y prime, and we're going to plug in 0 for t. And so it looks like C1 is going to be 2. Agreed? So we come down here, and then what's our other initial value? Y of 0 is 0. Okay, so y of 0 is 0. So that means plug in 0 for both y and t. So we're going to have 0 there. We're going to have plugging in 0 here. We get 2 times e to the 0 plus 0 times c1 plus c2. So that looks like C2 is 2. Yeah. So now we have both of our initial values, and they both were 2. So our particular solution, Say that once again.
Could you just add them together? Oh no, because it has a T.
That one has a t, exactly. So our particular solution will be y equals t e to the t minus 2 e to the t plus 2t plus 2. That is the solution for the initial value problem. Anything that's not making sense? Make sense? Good. Good, good, good. Yeah, do enough of these. You don't want to lose points on these ones. These ones are pretty fast. Pretty fast. All right, so let's get to our first real differential equations technique. First and only. So all we did so far was just integrate. We didn't really do anything special. So here we're going to have the first real differential technique. So when you're in differential equations, the idea is that you classify your differential equation and then you use the appropriate strategy. So the first strategy is if the differential equation is separable. And then you're going to learn things about how to solve a linear differential equation that's more complicated than ones that we looked at. Then you're going to learn something about exact equations and Bernoulli equations. Like, it's just a whole swath of different categories. And if it's this type, you do this. If it's that type, you do that. Like, it's not as complicated as it may sound. Solving differential equations, it sounds super complicated, but it really, if you know the technique, then it's not so bad. Some of the techniques are a little longer than others, but you'll find the problems shorter than some of these Calc 3 problems, Calc 2 problems. Okay, so this is our goal, and that may look really abstract right now. The goal is to put the dependent variable on one side, the independent variable on the other, and then integrate each side with respect to the variable on that side. So let's ignore that for a second. Let's just come straight down here and let me show you what this is trying to convey. So we have e to the 4t and y prime is dy dt. And when we look in here, we see two variables. We see the y and we see the t. The y is in the numerator of the derivative there, so we know it's the dependent variable. We have a dt in the bottom, so we know t is the independent variable. So right now the variables are all mixed on one side of the equation. What this is telling us, what we would like to be able to do, is have a situation where we can get, and I completely forgot. Let's move that over. So what we would like is to have all of the y's on the left and all the x's or t's, whatever the independent variable is, on the right. That's our goal, is to separate the variables. So that's what they're saying up here, that we can separate and get the dependent variable on one side and the independent on the other side. So right here, we can do that. And we usually leave the dependent on the left and the independent on the right. So that's generally what we'll do, because the dependent variable is in the numerator of the derivative. So why move it? If you tried to move it to the other side, it'd be in the denominator. So you usually just leave the dependent on the left. So dy, that's on the left, let's leave it. That's got a t, let's move it. So the way you move that over is like this. All right? Goes through the magic tunnel and the exponent becomes negative. And then how do we get the dt over? Just multiply. Everyone agree with that? So then we're ready to integrate. Now you can think about dividing this to the other side, but then it's in the denominator and we know to do the integration we need it up in the numerator, so it makes more sense. If you want to, you could think about multiplying both sides by e to the negative 4t. Right? That's one thing you could do, multiplying both sides by the same, and this is e to the 0, which is 1. So this is identical to that getting rid of negative exponents thing that we did. You multiply by the reciprocal. right? These are reciprocals of each other. And if you multiply a function by its reciprocal, you get 1. Now we integrate both sides. And so here's the part that's interesting. So this is a little different than the integral that we did before, where I said let's integrate with respect to t on both sides. Here we are saying integrate the left side with respect to y and the right side with respect to t. So a little bit different than what we did earlier. But on the left side, you're integrating to dy, and that's just y. And over here, we integrate this exponential, and we know that the integral of an exponential is itself. That's why it's such an important function. It integrates and differentiates to itself. And that is our solution. So this is a separable differential equation. Now, this was the easiest kind of separable differential equation because there's no other y's in here. So that's the next step up. We'll have it separate, but there's going to be more than just a y on the left. So this was a lot like what we'd already done. All right, so that is our general solution. Any question on any steps here? That is general because of the c. So now we look at this one, a little bit different. We see the dependent variable showing up in more than one place, right? There's y prime on the left and y squared on the right, so the dependent variable is showing up in a couple of spots. But our strategy is the same. Let's move the dependent variable off to the left, and let's move the independent variable off to the right. So first we're going to write it with differential notation instead of prime notation. And then we're going to end up with dy, and I'm going to write it as y to the negative 2. And then the x's move to the right, they'll become x to the negative 2 times dx. So we want our exponents, we want to have our functions in the numerator, so we'll have negative exponents because that's how we integrate. We need the powers of x or y in the numerators. All right, any questions on how we did that? So y prime is dy dx in differential notation. Multiply by dx. Then you're dividing by x squared, you're dividing by y squared, then you're moving them up to the numerators. Or you can think of doing what I said before. You can multiply this side by x to the negative 2, multiply this side by x to the negative 2, then multiply this side by y to the negative 2, and that side by y to the negative 2. Whatever your strategy, whatever works. Okay, so once we are in this situation where we have the variables separated, we're going to integrate each side with respect to the variable on that side. On the left-hand side, we end up with y to the negative 1 divided by negative 1. On the right-hand side, we end up with x to the negative 1 divided by negative 1. And we only need one constant of integration. So you can think of each side as having its own constant of integration, and then we're combining them. So in the end, we just need one constant of integration. All right, now that looks terrible. We want a function, ideally, that we can say is, so like y is equal to, that is not, we did not solve for y here. Ideally, we can solve for y. So let's see if we can solve for y. So that's our strategy, because the whole idea with the differential equation is to find the function that satisfies the differential equation. Well, we don't want to find the reciprocal of negative 1 times the function. We want to find the function. We want to get y all by itself. So first thing we'll do is multiply by negative 1. And let's clear out these negative exponents so that we can try to isolate y. So I multiply by negative 1, though. That c just absorbs it. A constant times negative 1 is still a constant. These two c's are now different, but that's not going to matter. We're never going to look back. We're just going to go forward, and anytime we have a constant times c, we're just going to write it as c. Just like a recycle bin. Just think of it as all the constants going together. Okay, on the right-hand side, let's get a common denominator, because we know that we are going to want to take the reciprocal of both sides. And as soon as we get both sides written as a fraction, then we can reciprocate. So now we can take the reciprocal of both sides, and we've done what we wanted to do. We wanted to isolate y. So this is called the explicit general, let me put the word general in there. This is the explicit general solution. So it's explicit because we isolated the y. We will not always be able to isolate the y. If you can't isolate the y, we're going to call that an implicit solution. So it's explicit when you have the y all by itself on the left. So that's explicit. And again, general is because we have a c. So if you were to take that function right there, take its derivative and plug it back in there, you would get a true statement. Get an identity. Any algebra issues? All make sense? No algebra drama? All right, let's go to another one. Okay, so the instructions say determine whether the following equations are separable. If so, solve the initial value problem. Okay, so when we look at this right here, let's first rewrite the left-hand side as dy dt. Now, so we know that we're going to want the t's to go to the right and the y's to go to the left. So we can instantly move that dt over to the right. And so the question then is, how can we get how can we break apart that exponential so that we can pull the y's to the left?
Set both sides to natural log.
Say that again?
Set both sides to natural log.
So if we were to take, and that's a great idea, because if we took the natural log of that e to the ty, that would pull the exponent down in front, and then we could divide. Yeah, that's partially a great strategy. What's the problem? If we take the natural log, don't we blow our differentials away? Because now, what the heck's natural log of dt? Right? So great strategy. That is exactly what we would do if we wanted to get the exponent down. But the problem is we've got these differentials, and they cannot be fiddled with. We need, in order to integrate both sides, we need a dy and a dt that are sitting out there, alone as kind of like factors. We don't know how to integrate the natural log of dt, right? We just need a dt and a dx or whatever the letters are. So good concept, but it's not going to help us in this case. Any other strategies? Okay, another great idea. So if we have e to the t times e to the y, what is e to the t times e to the y?
E to the t plus y.
E to the t plus y. Right? So that won't work. You could write it that way. You could say e to the t times y is e to the t all to the y. Does that help us? Can we break that apart? That thing's not going to break apart. That thing's like a diamond. That is not going to break. So multiplication up here in the exponent between the two variables is going to be unbreakable. We are not going to be able to separate here. So this is not separable. So when there is multiplication up there, that is a problem. Now, like Linda said, we could use this if there was addition. If there was addition, if that was addition right there, then we could turn it into e to the t times e to the y. And then we could divide the e to the y to the other side. So if there was addition instead of multiplication, we could use that strategy and it would work beautifully. So it's not always obvious that something is or is not separable. So it is going to take a little bit. This is typically the problem if you have both variables multiplied together in an exponent position. Because you can take away a sum, but you can't break apart a product. All right, so that's not separable. All right, you all try this one. So try 20. So see if you can separate it. What are the chances of me putting two non-separables in a row? So see if you can separate it and find the general solution. Let me know if you need any nudging. Think about it, a way that you could get that constant in the exponent position down in front. Yeah. On the right track. You're going in the right direction. Absolute value wise. Oh, you're fine. So right here, we're going to get you're on the right, you are flying along. There's going to be one subtlety with getting rid of. There's something with the constant on the other side. Can you bring it down in front?
Just based on not that bad, but still.
It's going to be multiplied. So if you have C in the exponent position, it end up being a multiplication.
We have like maybe two problems. Well, 90% of it was
Yes, it is close. There's still one more thing we can do. When we get the general, yeah, the C, so with this absolute value here, we're going to want to find the explicit solution. So we're going to do some exponentiation.
This is the method
You say you need help? So
Yeah, there you go.
that y right
Yeah,
there,
everything
needs,
is-
so this is the y prime.
That's
Yeah, so we can't, yeah, we can't do this. We can't do
I
this
don't know
because
whether
we
it's
have
trying
y
and getting a
from t
super
to
wrong
omega.
answer or not trying.
So we need to, when we, the first step is going to be to write the y prime as dy dt.
Problem is, I
And then put the y on the left by dividing by it, and then the dt on the right by multiplying. So on this side, you still have just your y times.
Yeah, you're
See,
See, that's it.
I know this guy. There you go.
And now this dt can jump over there, and these y's can jump over there. Or, excuse me, this y can jump over there, and this
No, no, I got
dt
the
can jump over there.
there.
Yes, exactly.
No, no,
Yeah,
I got
that's
it.
right. And then integrate both sides.
None of these.
No, there's two different.
Does that mean zeros?
All right, let's see. So what was your concept? I'm curious. Okay, so first step is always to write your y prime as dy d whatever. So in this case, dy dt. So that's our first step. So if we are going to be separating the variables, if that's the strategy being used, you need to turn the y, you have to go from prime notation into differential notation. That's the first step. And so once we get into the differential notation, then we can put the dt on the right with multiplication, and we can put the y on the left with division. So this is going to be the separation of variables. So now the variables are separated. T's on the right, y's on the left. And here's where we can integrate both sides. And it feels a little funny because we're integrating one side with respect to y now and one with respect to t, but it works. So on the left, we get natural log absolute value of y. Natural log absolute value of y. On the right, we get exactly what you think we're going to get. Okay. Now, right now, we do not have y as an explicit solution. Y is hiding inside that natural log. So we want to get rid of the natural log. We'll deal with the constant at the very end. Say that again? Let's chuck an e at it. I think that's a great idea. Chuck an e and see if it sticks. Chuck an e. So that whole right side now becomes the exponent. Now, we've got this absolute value of y. Absolute value of y is either y or negative y. Right? It's one or the other. And we want to get to just y. And so here's the clever strategy. On the right, we can use that exponent rule that we just used a moment ago. Isn't this true? You don't like it? Right? If you have e to the a multiplied by e to the b, you add the exponents. So we're kind of going backwards. Does everyone see that? Now e to the c is a constant. And it's now a multiplicative constant. So it now has jumped down from the exponent and it's turned into a multiplicative constant. And we just said that absolute value of y is either positive 1 times y or negative 1 times y. Positive 1 and negative 1 are multiplicative constants. So we can now, up here we have absolute value of y. Now we can say, oh, well, let's just take that plus or minus 1 and let it merge with that constant. So this constant may be the same if this is a plus y, but it will be exactly opposite if it's a negative y, if this y is negative. But that's okay. We never look back. This constant will now work for this equation. This is the explicit general solution. So it's explicit because we solve for y, and it's general because we have the c. And usually they're going to ask you for the explicit general if you can do it. Sometimes you can't isolate y, but most of the time you can. So the one new, well, it's not new, it's law of exponents, but this is a strategy that you will see repeatedly. Turning that constant up in the exponent into a multiplicative constant out in front. And once that's a multiplicative constant out in front, it can absorb the plus or minus 1 from this absolute value. So now we have our initial value to deal with. So y of 0 is 4. So let's come over here. Y of 0 is 4. So we're going to plug 4 in for the y. We're going to plug in 0 for the t. E to the 0 is 1, so we get that our constant is 4. So therefore, we are going to have y equals 4e to the t to the 4th plus t. So that will be the particular explicit solution. So if you can solve for y, then it's explicit. No. Because the question will say find the explicit solution. Yeah, so you don't have to say that it is. Yeah. All right, any step there? Everybody okay with the algebra? All things algebra come to the surface in Calc 2. All right, start number 23. See if you can separate that one. Notice that the exponent's a little different than the one that we couldn't do. Yeah, those are separable. Oh, yep, that's fine. That's fine. I want to see what you're going to do with this, though.
Yeah, I'm trying to figure that out right now.
So this is not going to be subtraction. Yes.
Subtracting y is
So that's going to be e dx over e dy. So that's, yeah, multiply. Yep, that's right. So where's your dy? So there's. Oh, you've already integrated. You've already integrated. So the integral of this side is just e to the y.
This.
Because that dy is the difference. And the integral of this side is just e to the x. No, that looks fine. That looks fine.
But I don't know how to get from there and see.
Oh, wait, where is it from? Hold on. So when you take the natural log of that sum, you can't break that apart. You can break apart a multiplication of a log of a product. Right, log of a product you can turn into two logs that are added. But this is the log of a sum. The log of a sum you can't distribute a log across a sum. You know what I mean? You see it? So you did. Yep, yep, now it is. And then plus C. Plus C in there. Yes, exactly. And then you're multiplying it.
Oh, right, because it's not.
So you have ln 3
And then solve for y. Solve for y.
I don't know how
You didn't read that one?
I'm got the same answer.
You are right. Because this here, but this puts it positive.
Well, I don't know.
Oh, wait, no, sorry.
This part.
So it should utilize x plus
And plus the natural log of
Yes.
So you can just say you subtract one constant and the other. Zero, and it's still a constant. So you only
I know.
maybe.
All right, let's go through this one. So the strategy here, the thing that you want to make sure you're seeing clearly is that this law of exponents turns it into that. So e to the negative y puts it down in the denominator as e to the plus y in the denominator. Right? If you have exponentials with the same base, you subtract vertically, x minus y. And now we can cross multiply pretty easily, and we're going to get this. So that is going to be our separation of variables. Here's where we integrate both sides. And on the left side, the integral of an exponential is itself. On the right, the integral of an exponential is itself. Then we have our constant of integration, one constant of integration. And we now have an implicit general solution. It's implicit because we haven't isolated the y yet. But we can isolate the y. If we take the natural log of both sides, bless you, we now have the explicit general. So this is explicit general. And there's nothing we can do there. We can't distribute that log. That's it. That's as far as we can go. There's no more simplification here. If it was the natural log of a product, then we could separate it into a sum. But it's not. So we have to leave it like that. All right, so there is the first part of this. Now we go to our initial value, and we're told that the y value is natural log of 3 when the x value is 0. Okay, what is the next step here to get to the c? So how do we get rid of the natural logs? So we exponentiate both sides. We don't just cancel them. I mean, essentially that's what happens, but don't do something like this. This is not how they're going away. We are not dividing out ln. Right? The mathematical way is to exponentiate. So we put each of them as an exponent on e. So that's called exponentiation. And when we exponentiate the left side, this becomes just 3. And when we exponentiate the right side, it becomes 1 plus c. So c is 2. The other way to think about this is if the natural log of, say, a equals the natural log of b, a and b have to be the same. If natural log of this is natural log of that, then this and that must be the same. Mathematically, to get to that statement, you exponentiate both sides. Don't divide by ln. That would be bad. Okay, so therefore, we have our particular solution, natural log e to the x plus 2, all in parentheses. That is our particular explicit solution. All right, so let's go through this one together. So again, the only strategy that we're using in this class is separation of variables. And so it's always a good step to first rewrite any y prime as a dy dt or a dy dx, depending on the independent variable. So we have to be in this differential notation in order to separate the variables. And obviously, we can put the t's on the right pretty easily here, and the y's on the left pretty easily. So we're going to divide the y's over and multiply the dt to get it to the right, but then divide the t to get it over. So now it's separated. Now it is separated. What integration technique will we use for that first integral? We have a factored denominator. PFD? Factored denominator means partial fraction decomposition is going to work very nicely. So we have a factored denominator, so that's great. So we're going to integrate both sides here. And let's come off to the side to do that integration. So let's just come off to the side. We're going to integrate. Actually, let's just go right through our PFD stuff. So we know that we want to rewrite 1 divided by y times y plus 1 as a over y plus b over y plus 1. We'll find our constants off on the side. So to find those constants, we multiply by the left denominator. Multiply everything by the left denominator. And when we multiply by that left denominator, that is our equation. Of course, we're going to go to convenient values. And those convenient values are 0 and negative 1. The convenient values are always the zeros of these factors. Plugging in 0 across the board, a is 1. Plugging in negative 1 across the board here. When you plug in negative 1, the a term here is going to disappear. Negative 1 plus 1 is 0, so that's gone. And we end up with 1 equals negative b, which tells us b is negative 1. So now we know how to rewrite the integrand of the left-hand side over here. So we're going to rewrite this integrand as a, which is 1 over y, and then minus 1, so minus 1 over y plus 1 dy equals 1 over t integral dt. Now it is integrable. Now we can get natural log absolute y minus natural log absolute y plus 1 equals natural log absolute t plus c. right. Any questions? Lots of logs. Lots of logs. Okay, so our goal, this is a general solution in implicit form, because the y is buried, it's not isolated. So we want to isolate the y if we can. So somehow we're going to have to merge all this stuff together if we're going to have any hope of finding the y. So we can use a log property here. So this will be log of this. All right. So log of A minus log of B is log of A over B. Now we can exponentiate both sides. So we're trying to unravel everything that's on the outside here that's attached to the y's. So we're going to exponentiate both sides. So remember, when we exponentiate the right side, the entire right side is getting boosted as an exponent. The whole right side becomes an exponent. Can we use an exponent rule here? Yeah. This is going to be e to the natural log absolute t times e to the c. E to the a times e to the b is e to the a plus b. Okay. E to the c. What should we call it? C. All right, so we're going to call e to the c just c. Let's just stay on this line for another moment. And what about e to the natural log absolute value of t? Absolute t. Because e and natural log cancel each other. All right. So now we have this left-hand side, and we have this right-hand side. On the right-hand side, we have a multiplicative constant. On the left-hand side, we have an absolute value. The absolute value of something is either what's inside or -1 times what's inside. Well, if this is a multiplicative constant, it can absorb the 1 or the -1. So at this stage, we can eliminate the absolute value on the left. We could say that. Can't we also eliminate the absolute value on the right? Absolute value of t is either t or -t. And again, that plus or minus 1 can just be swallowed up by the constant that's sitting in front of it. So we could get all the way down to this. So this c is just gobbling stuff up. All right, because absolute value of t is either t or -t, so it's a constant times t in either case. And that constant can get sucked into that. Now we're back to algebra something or other. Algebra 1.5. We haven't isolated t yet, excuse me, y, but we can. How are we going to isolate y? So we're going to multiply, we're going to separate, we're going to get the, so if we, let's go this way. So if we multiply both sides by that denominator, let's distribute at the same time. We can distribute at the same time here. So multiply both sides by y plus 1. You're going to have ct times y. You're going to have ct times 1. And then subtract, factor, divide. So then we subtract. In algebra, we would say collect like terms. So the two y terms get collected on the left, and then we factor, collect, factor, divide. Collect, factor, divide. And now we have a general explicit solution. Twice. It's getting worse. It's twice as bad. All good with that? Algebra, algebra, algebra. And did this one have initial values? Where was this problem? Y of 3 is 1. So y of 3 is 1. Y of 3 is 1. So this tells us that the y value will be 1 when the t value is 3. So t value is 3. So we have that. Now we have to solve that for c. Looks familiar. We've got a stacked fraction with a c in both places. Multiply, subtract, factor, divide. So we get back to algebra again. So we've got that. So that's going to be 6c equals 1. So that will be c equals a sixth. So we are going to plug that in. So our particular solution, we're going to plug in 1/6 here. This is our particular solution. Fraction's no good. We can't have a fraction of a fraction. That is not simplified. So what do we multiply top and bottom by? 6. If we multiply by 6 over 6, that will simplify it in one fell swoop. So 6 multiplied across the top gives t. 6 multiplied across the denominator gives 6 minus t. So that will be our final answer. Multiplying by 1 yet again. So multiplying by 1 in the denominator, or multiplying by 1 in the denominator, we have to distribute that 6. Okay, someone must have an algebra question. I would think. Any questions on the initial value part down here? That algebra is very similar to the algebra up here, although here there's less going on, so maybe it's more obvious. How about the algebra up here? Any questions? You good? All right. I'm so glad you get it all. All right, we only have a minute left. So what I don't want to solve this problem, but I want to remind you of 2 words that we're throwing around here that may not be 100% something that you remember clearly. So when you look at that equation, as you all know, is a unit circle. Is this a function? No. And when we say that word, there's some hidden stuff going on. By that we mean, is it a function of x? If somebody just says, is it a function, we automatically default to x being the independent variable, which is fine. We just have to be aware of that. So this is not a function, but what it has is 2 implicit functions. This is a function. Right, that is a function. And the lower half is also a function. So that curve, we would call it a relation. So a relation is just any squiggly curve thing. It doesn't have to pass any tests. This relation has 2 implicit functions in it. So we'll talk more about that next week on Tuesday when we start doing our review. And we'll finish up these last 2. Work on these 2 over the weekend, and we'll finish them off beginning of class. But just keep this terminology in mind. So a relation can have embedded functions within it. You cannot always find the equations for these implicit functions. So in this case, we could actually find equations and use those as different. You cannot always do that. Have a great weekend. Work on those worksheets. Get the corrections done for chapter 6. Get chapter 8 one started. The first question on chapter 8 is probably the most tedious.
When is it the?
Test corrections are due Monday night by midnight.
Test corrections within the.
Not test corrections, worksheet corrections. Worksheet corrections. And then the worksheet for chapter 8 is due Tuesday. But I'd rather have you have it done on Tuesday so you can be studying for the test on Wednesday.
Yeah, obviously.
We know what we want. Stop this.